Okay, so yeah, so I'm just gonna put it out there that with a question mark, it really is a question. Start with a question mark, and we have some little bit of success here and there. So I'm just tell you a little bit about that. But before I do, I would like to coin a phrase, central dogma in the mind of a physicist or biophysicist, whatever statistical physicist. What is machine learning all about? And then I'll go on to a couple of results that recent one and the not published one. to show and to demonstrate and to convince you that we actually can help. Okay, here's the central dogma. Obviously, it's because my background in biophysics. I mean, obviously, this crowd is not unfamiliar with that notion that number 3 is very important. There's three very important things to remember. One is the training data, right? So you start with a set of training data, and you train a model. The middle box is a model. In this case, it's a neural network model, right? And you train it, how do you train it? You train it by optimization, optimizing some global loss function. And by training it, you learn, training is also called learning, and you learn a set of parameters that actually can fit the training data very well. That's the optimization part. And then, okay, you have a model, and you can explain the training data, but the real test is generalization, what people call it. Now you have testing data. Can you actually do well in the testing data, right? So that's called generalization. Whether your model can be generalized to data you have not seen before, that maybe corresponds to the same distribution, right? So that's generalization. How do you actually build a more accurate predictive model? Is to find a generalizable solution, and often that people use in computer science is actually putting some kind of regularization to try to help you find a better solution, right? What they generally call regularization. So the two questions in deep learning, I mean, is what makes a solution generalizable, and how do we actually find them, right? So to this end, I mean, physicists may not be used to this notion of generalizability. Let me just give you a quick summary, one slide, that this is a chart that Jose is very, very familiar with, right? Jose, you probably plot this very plot, right? Okay, so this is the Jose's energy landscape in the protein folding space, right? This is some reaction coordinate, real physical coordinate system. And you see that this is the landscape of energy, and there's a unique solution to this problem. There's actually the most stable native state that corresponds to the minimum of this landscape, right? There is a unique solution, and it's very difficult to find, all these business protein folding. Jose spent all these years. And the question there is really, how do we find the solution, right? Machine learning is very different. And so this is an over-constrained problem, if you wish. Deep learning is taking another route. Say, okay, I'm going to put in tons of parameter. We heard yesterday 195 billion and more parameter. In this high dimensional space, my landscape totally changed, loss landscape. Instead of having one solution, I have many solutions that have equally good loss function, right? So the question now changed. Solutions are easy to find. They are abundant, I will show you. But the solution now, the question becomes, which solution is better? Better in what sense? More generalizable. Once you have a test example comes in, you can do well. Okay, that's the challenge for machine learning. So to this end, I'm going to tell you two results. One actually in the opposite order. One is actually, how do we find it? How do you find a solution or a better solution? And in this case, basically talking about stochastic learning dynamics in deep learning. I will convince you about two things. This is going to be very quick, the first part, because it's already published last year, so you can take a look at this paper. So what two things you have to understand is, from this first part, is the noise in the machine learning dynamics is a smart noise. It's not a dumb physical thermal fluctuation. Okay? That's the first notion. And because of that smart noise, you have this inverse variance flatness relation, which we actually call the inverse Einstein relation. So you'll see a little bit later. Okay, so a toy problem. Once you enter into the realm of machine learning, as a physicist, you always want to find the toy problem to work on, right? The toy problem work on is the MNIST problem. the classification of handwritten digits from 0 to 9. You have 60,000 images of these handwritten digits. The task is basically try to identify an image and see if it's 0 or 1 or 2. That's classification. And the model is basically a feed-forward neural network with hidden layers, 2 or 4, and so on. So this is the input, this is the output. Sitting in the middle are the weights, are the parameters in your model, right? So the task really is just to find the parameters in your model so that you actually can give you an image input, you can give the output, which says,
input is what?
Sorry?
What is exactly the input here?
Input is the pixel, 20 by 28 by 28 pixel, all the pixels in this image.
So each box has 28 pixels.
Each of this image has 28 pixels. 28 times 28 pixels.
The full 9 or each one? Number 5 has 28 by 28?
Exactly. Okay. Each image has the same number of pixels. Okay, so of course, this horse is a problem, has been beaten to death many, many times over. That's not the issue here. The issue here is going back to the question. The issue here is that we as a physicist would like to help find out how the horse actually died, right? So, okay, so what is a machine learning for a physicist? Going back to the same question, is basically you have a output, predicted output, depending on the input and some parameters. You want to find the parameter based on a loss function. Basically, it's a measure of a distance between your output, predicted output, and actual output, right? The distance measure. D, in this talk, I just use cross entropy loss. You can use mean square loss and all that kind of losses, okay? Of course, physicists know how to do this problem. We just go to the gradient descent, right? So just go downhill with the loss function, and that solves the problem. There's two problems with this approach. One is that it's too clumsy for a large data set. It's very hard to compute the loss function for all the data that you have, right?
What's Z?
Z is the actual real output. Okay. All right. So that was the motivation for people to develop what they call the stochastic gradient descent. Is that at each time step you go downhill, not with the loss function constructed with the whole data set, but a subset of the training data set, okay? Called mu. So that's called L mu. So basically that's the gradient descent. And you can write down the gradient descent dynamics with a Langevin equation approach. Actually, Pratik and Suato, Pratik here and with his advisor, Suato was the first one actually to write down that equation. It's here. So you can write down that equation. And the noise here is not just your thermal. This is the claim. The noise is neither homogeneous nor isotropic. Where does the noise come from? It comes from the difference at each time step you subsampling. It comes from the difference between at any given instant, the loss function for that particular subsampling and the average, right? So that's the noise. So the noise has a lot of structure in it. So it's neither homogeneous, it varies, depends on the weight, the weight parameter itself, and the most importantly is isotropic, non-isotropic, not isotropic. So it's a tensor. The noise can be captured by a tensor that varies in space. So here's the intuitive picture of learning dynamics. It basically is naively described by this Langevin equation. It's a high-dimensional drift diffusion with funny non-homogeneous noise. Funny means it's non-isotropic and so on, right? But I would like to convince you two things. One, it's actually not a high-dimensional drift diffusion. It's actually low-dimensional drift diffusion. Second, instead of being funny, it's actually very smart. This noise is very smart. Two things. The first point is actually drift diffusion in low dimension, basically based on very simple PC analysis. You look at the dynamics of the wave moving in a very high-dimensional space. You look at the fluctuation, and you do PC analysis. Pretty quickly, you see that most of the variation happens in the top 40 dimension among all the 2,500 dimension, right? That's a very clear signature that most of the dynamic, the search dynamics, happen in a low-dimensional space. The second point I try to make is that, okay, now you have by PCA or by some other method, you identify the direction in the parameter space, and you can look at the landscape in those dimensions, in those directions, right? Now you have a coordinate system, And you look at the loss landscape in those directions, and you characterize the landscape in that particular direction I by what we call the flatness. The bigger the F, the flatter the landscape is. Okay, that's just the definition. And you can compute that. So on the top is for mode 1, 2, 3 to thousands of mode. And you can calculate each direction, the flatness in that direction. And on the lower plot is what you've seen before, is the fluctuation of the weights in that direction. Okay? So you see immediately there's an anti-correlation here. And if you plot one against another, you get the inverse relation, what I was talking about. The variance in that particular direction is inversely dependent on the flatness. The flatter it is, the smaller the fluctuation. Isn't that odd? So as a physicist, you should find this very, very surprising. So that's why we call it inverse Einstein. Usually, if you have a sharper landscape, flatter landscape, the fluctuation would be larger. But that's under the intuition that it was a constant temperature. Here, I'm telling you is that the actual temperature, the fluctuation, is actually dependent on the landscape.
What is the definition of epsilon? How do you define epsilon?
Oh, in this case, we define f of I by just it's a nonlinear definition. It's not the curvature here. It's defined by how far do you go out before within which the loss actually increased by a factor of 2.
And this is for which dimension?
Any dimension. So f of I is in I dimension, flatness in I dimension. So each dimension, you have a one-dimensional landscape, and you just look at the flatness in that particular dimension.
Just curious, the actual data that you're showing, is that for full MNIST or is that a two-class problem?
Oh, full MNIST, yeah.
Do you know why there's just a single, there's that the sort of bulk distribution and there's this one point?
That's the drift.
Okay.
That's the drift. That's why it's called drift diffusion, right? So if you have a drift, the PCA will tell you this direction is very large because it's actually not diffusing, right? That's the drift. That's a good point, yeah. Okay, so I leave you to, so last slide for this particular part, right, we're gonna get to the second part, which is new, is that the smart noise part. If you think about noise being sort of something you can control, there's a very famous thing called simulated annealing, that as things progresses, you slowly cool things down with some prescribed schedule of how you cool down. This thing is doing it, but in a very smart way. It's doing it based on where you are. If I feel my environment has become flatter and flatter, I cool down. I don't fluctuate as much. And this is a tensor, so in the particular, it actually can tune it in a particular direction. So it's what we call a self-tuned annealing algorithm to find flat minimum. Because why flat is better? Because at the flatter minimum, the noise is minimum. So I like to stay in a cool place. So that's just the argument hand waving. You can look at our paper for more technical details. So here's the slides that I paraphrase from some famous author. Oh no, oh well. It says all solutions are equal in that they are being the minimum. But some are more generalizable than others, right? And we find the flatter minima is more generalizable. That's just we didn't propose this, many people proposed before us, but in this study we just find why actually SGD was able to find those flatter minima. All right.
Fast comment here.
Yeah.
Do you know that this is also true in protein folding in a certain way? On the structural prediction, when people are minimizing and they have multiple options, they tend to say the one that's more funnel-like, broader funnel, tends to be the easier solution. Actually, David Baker is the first one that got this idea from funnel to the structural prediction. So it's an interesting story that this is generalization.
Yeah, we should. Yeah, in terms of that's in terms of pathway. How do you get there, right?
In these networks, both the bad minima and the wide minima are all connected to each other. So the zero level set is completely connected and just happen to be in different parts of the lake. I don't know how it is in protein folding.
Yeah, so this again is a dimensionality problem. I think with a high dimensionality, all these minimum, as Pratik was mentioning, it actually seems to be connected, but connected in this other dimension that maybe in protein folding it does not exist.
I have to think about what connected means.
Yeah.
But there is a connection between them because they can.
By connection is that you don't need to go through any barrier.
I know exactly what you're saying.
Yeah.
The question is how many dimensions you have to do that. That's a.
Yeah, exactly. That's the dimensionality problem. I think these other dimension, I think is.
Can never be true. See, protein fold is a physical problem.
Yeah. That's not true. Exactly. So going back to yesterday, there was a question about 1 million dimension. By using symmetry, you eliminate 10. It's not useless. That's just wrong because I think it's wrong because really relevant dimension is maybe 20. So eliminate 10 is great. I mean, so,
That's like a local statement though, right? It's not.
yeah, it's not clear. But I think what I'm trying to say is that what really matters at the end of the day is very few number of dimensions. But so eliminate those relevant dimensions by whatever number. It should not be compared to the overall 10 million dimension. What I think, what I believe, this is my speculation, is that all the other dimensions are being used to try to find those true solutions easily. Just
But
give you a shortcut.
But that's an interesting comment, just to start on your question. If you do, for example, the random heteropolymer, if you do in 2 dimensions, the chain crossing problem is a nightmare.
Exactly.
In 3 dimensions, it's doable.
Yeah. But you cannot go to 4
dimensions
dimensions.
or more, there's no problem.
There's no, right. That's basically, I think that's what the analogy goes. Yeah. So, okay, second topic. What really makes the solution better? I tell you that the flatter solution is better. I'm just waving my hand. I'm just, talking to people in the field. So to me, I really want to see how actually, intuitively I know. I just want to make my intuition more solid. So there's the effort from that. Basically, based on something that we found, which I think is really, really cool. It's an activity weight duality that I'll show you. It's an exact duality, which I find quite surprising. Nobody, at least as far as I know, has mentioned that. Okay, here's the issue. As I told you, there are multiple minimum with the same height, same really global minimum in that sense. They may be connected in other dimensions continuously. I'm just plotting in one particular dimension, the different solution. So the issue is that how do we characterize generalization? How do I characterize the generalization performance? Well, one way to do that is actually to say, well, at this particular solution, if I use instead of the training data, this is the training landscape based on training data. I use the test data, but I use the same weight. And I look at the solution and to see how would the testing data perform with the same weight, right? So I define this as a generalization gap, loss function. That's a delta L, so basically it's defined formally here. I don't know how to calculate it. Well, you can put in the computer and just try it. But wouldn't it be nice if I could compute it by the following transformation? So this lives on 2 different landscapes, right? One is training data, one is test data. Wouldn't it be nice I find an equal height on this training landscape, which I have studied a lot because that's how I used to train. By shifting my weight to a point that actually the height, the loss function doesn't change, right? I shift. So by changing, in other words, if I sort of find a duality between changing data and instead of changing data, I change weight. Of course, the change of weight will depend on the data, right? If I find such mapping, then I can study everything on this landscape, right? On the training landscape, which I know a lot.
There must be lots and lots of dimensions in which you can achieve the same thing.
Perfect. See, the dualities, that's the pearl. So exact activity weight duality in a fully connected network. Layer, not network, layer. Any layer exists such duality, and many of them. That's actually pretty trivial in some sense if you realize it. Neural networks operate in a linear, nonlinear fashion. You first sum up the activity in the previous layer in a linear fashion with weight, and you sum up to be what we call A, the pre-activity property, A, for A of J for this next layer, and you put a nonlinear function on top of it, right? Be ReLU or whatever, sigmoid phi is a nonlinear function. You don't want to mess up with nonlinear function to find duality. But this is the linear part, right? So I can certainly find, so if my data has changed from x to x prime, right? If I want to evaluate x prime under the same weight, I can say, well, if I don't change the data, but I only change the weight, can I get the same sum, same pre-neuron activity, A? Of course you can. W prime, you have n1 times n2 in the fully connected network. And you only have to satisfy, n2 constraint, right? Of course you can. And then not only you can, there's many of them. So this is the join. So in the z-axis, it's the data, right? In the plane is W, is the weight. It's just a simple cartoon plot. So you try to evaluate the loss at this point when you don't change the weight, but you change the data. The claim is that in terms of loss function, all the points on the dotted line have the same loss as this guy, right? So this claim means that you don't change the data, instead you change the weight. Okay, not only you have many, you also have, so what we in the whole following analysis, we used a special one. How do you pick a special one? Well, we picked the special one that is the closest to the origin. We find one that had the minimum distance away from the actual solution. So we call this W prime the dual weight for the new data X prime. The dual weight, the smallest, the delta W minimization will give you actually very simple expression. Remember delta W, the change in the Wij is a linear combination of all the other weights, and the prefactor depends on data, delta X and X itself. All right, so now we actually can compute this thing now based on the training landscape, right? We have a training landscape like this. For each data, you have different landscape. On average, you go back to the blue one. But what you have now is all these dual weights. For each sample, you have different dual weights. So you have a distribution of the dual weights. And you calculate the expected value of the loss by using the landscape of the training data, right? So, I mean, there's a lot of math going on here, but eventually you get to, and you can do it, you can decompose in different directions, right? So at the end of the day, you get delta L, the generalization gap, is equal to this formula. I'll show you next slide. So decompose into different dimensions, m is the number of weights in this layer. In each layer, in each direction, it corresponds to two things. Sigma Wn, I'll tell you what it means, and sigma G of n. Sigma G of n sort of measures, or if you wish, rigorously, highly correlate with the sharpness of the loss landscape. The bigger it is, the sharper it is. Basically means that there's an effective gradient here which is larger, okay? On average, right? If you perturb around the solution. Actually, you can show that sigma square is equal to the Hessian plus a order delta x squared. Delta x is the difference between the training data and the test data, right? And the other one is the spread. Describe the spread of the dual weight in that dimension, right? That's the standard deviation of the distribution in that particular direction. And that is actually, you can write it down. The norm of this fluctuation of the dual weights actually is a distance measure of the the actual solution itself to the origin, weighted by this distance metric, which depends on data, right? Delta x squared kind of order. You actually can, yeah. All right, what do we use this for? Now you can actually try to understand, using this formula, you actually can understand where that generalization, what control generalization. There are two things, sigma W and sigma G. The sharpness, but also sigma W, which correspond to roughly the size of the solution, if you wish. So the claim is that learning rate, if you remember in SGD, you have a learning rate, in the learning dynamics, you have learning rate, you have batch size. I think these two things work sort of symbiotically. But if you change learning rate in a range, the bigger the learning rate, create a bigger noise in terms of amplitude. And actually, a result, so alpha is increasing in this direction, and this is the sharpness measure, right? Sigma G actually decreases the sharpness in the top sharp direction. So it actually allows you to find flatter solution. And that's the reason you get generalization laws that go down, right? This is a black dot, go down with learning rate. At least, of course, if you push it further, you'll diverge. So in this region, it actually helps to have a bigger learning rate. So, okay, on the other side, to demonstrate the effect of other factor, the size of the solution, there's also another trick called the weight decay. So if you increase the weight decay, another regularization, what you find is that it doesn't really change the solution structure. Its sharpness spectrum doesn't really change. But what happens is that the size of the solution get reduced. And as a result, your loss goes down, right? So within certain range, again, beta, the weight decay also helps generalization, but in a different way by reducing the size of the solution. Okay, so that's it. So let me put this up as a summarization of what I'm trying to say is that, okay, here's sort of, there are two approaches to tackle machine learning or deep learning. One is sort of an engineering way, very effective. They have all the tricks, but it's trial and error, very specific, not very general. But there's also a mathematical way, very rigorous, but in some cases, may not very practical. They insist on proving theorem, which I don't like. But I don't know how to do it, but that's why I don't like it. So we really need a middle way to approach this based on statistical physics. Intuitive, semi-rigorous, actionable insight, right? And here are all the things that I talked about, but in the future, there's all kinds of issues we can tackle using this new statistical physics-based approach. Transfer learning, robust learning, as you heard yesterday from Arena and Rish. So I think with that, I thank you.
Thank you. So we have time for a couple questions. But before we go, I'm going to tell you that I'm going to take prerogative. They gave me the microphone as being chair. And I'm canceling the break because there's no point to having a break, and that gives a little flexibility for our speakers. Okay? So if you want to get some coffee, you can stand up and pick up coffee and come back. I think it's going to be more interesting. So we have time for questions.
Can I ask a question? Sorry, I'm online today.
Sure.
Okay. Yuhai,
You abandon us? You abandon us?
I did. I apologize. I have to be in two places at the same time. Yuhai, I loved this talk. I've been tracking a lot of algorithms that appear that sort of tweak or play with noise. They add noise to the gradient in various forms by some stupid schemes. And I've been thinking for a long time of a reactive scheme, which we have used in protein structure sampling rather than get stuck with a sort of a cooling regime or a fixed regime for simulated annealing, doing something a little bit smarter. But anyway, my question is not on this. My question is, I keep also reading a lot of papers on saddle points. Michael Jordan had a 2019 paper showing how to efficiently get out of a saddle point. And there was an algorithm called perturbed gradient, which was nothing really. I mean, you just add some noise to the gradient, a very rudimentary algorithm for computer scientists. I didn't hear you mention the word saddle point, and I did get lost when you talked about all the minima are in a lake and there are no barriers. If you can help me a little bit clarify it for a computer scientist like me with very little statistical physics background, that would be great.
Yeah, I think in our experience is that we don't encounter the problems. I put saddle points up there for just the motivation, the possibility. If you really, indeed, if you just really just have gradient descent under some condition, you actually will run into that problem. But in SGD learning, I think nobody has been bothered by saddle point per se. And actually, there's some earlier work by Ganguly and all, and which shows that actually, you really don't have that problem not a very severe problem. So I think part of the reason is actually because dimensionality, right? So you may have saddle point in a few directions, but you have many other directions that you can allow you to go down. So in this problem, as I said, in physics, we run into that problem. But here, maybe because over-constrained nature of the physics problem, but here you just have so many degrees of freedom, you can always tunnel through, right? And by tunnel through, I mean those flat directions are the places you actually tunnel through.
All right, so we have one more question here. Why don't we change computers while you answer Herbie?
Okay.
So now that you solved the problem of deep learning, I'm going to ask you about solving other problems. Well, I mean, or maybe say it differently. So your connection, your duality seems very specific to the way in which neural networks are currently used in terms of this linear, nonlinear function. So going forward, I mean, how would you do this for some other example of learning, which maybe the first part of your talk still applies to, that maybe evolutionary learning, I mean, biological evolutionary learning, maybe there's some language in which it's similar, but the second part is clearly very specific. So I'm just wondering if you have any thoughts on this.
Okay, I think it's very specific because of the exact nature of this duality and the simple linear nature of it. But I think the idea of a duality is probably general. It just relates to the fact that you are looking for maybe even approximate duality, if you wish, will be useful, because that basically is some kind of correspondence between the input and your parameter. And for example, I would go one step further, saying that the flat direction I mentioned, is the direction in the weight space. If you use my duality to map back to the input space, that's actually is a symmetry. So by using this kind of approach, I think it goes beyond what I can do here because I can explicitly write down the duality. But having that duality in mind, and even looking for other cases you cannot find exact duality, find an approximate one, will actually help you. So I think that's a general approach. For the first question, dynamics, yes, but I think SGD noise, how general that is, I think it may be the subsampling, and I mean, it's basically based on subsampling.
Let's leave that for the discussion. One fast question, one fast answer before we start.
Sure, yeah. I was curious, so that, like, this gives a prescription for optimal hyperparameters, I guess, these plots that you showed of, if you believe it right, this, you want to minimize the spread and make the gradient as small as, or the Hessian as small as possible. Does that prescription work well?
Well, we tested, well, we didn't test well, at least it works well in the sense of alpha and beta, the learning rate and the decay rate. But I think there's another thing. I told you that the learning rate, for example, if you push it further, you go to another regime, will diverge. You cannot use
Sure.
right?
Yeah.
So that we can know. And also, it works well in the sense that, for another case, that you have dropout, for example. The dropout, actually, I didn't show this plot, has a funny thing. The dropout initially makes sense, but eventually it doesn't. So you have a U-shape dependence on the dropout rate.
Uh-huh.
So that actually we can explain it based on this decomposition.
Okay, we are going to have a big discussion. Let's go to the second view.